Hello class, I'm back with another pre-recorded lecture. Today we're going to talk about Laplace transform, and it might be a new concept for you. Let me tell you my own story. When I was in your shoes and I was taught Laplace transform, it was a part of a course called Mathematics for Engineers. And we learned Laplace transform in the context of pure mathematics. So we weren't exposed immediately to its applications. And that's why so many equations, so much mathematics, we felt kind of bored. But the good news is in this course, we get to use Laplace transform as a tool. So we learn immediately the applications of Laplace transform, and I'm sure you appreciate how Laplace transform will simplify solution of ordinary differential equations. If we look at our course navigation slide, in terms of progress, we are here. Most recently, we were able to solve a first-order linear ODE using the analytical method of integrating factor. Through this session and the next couple of sessions, we will try to extend the analytical solution for more general form of linear ODEs. And for that, we will use Laplace transform. As I said, as an engineer, it is much easier to understand the concept of Laplace transform when we know what is its application. Let's say we model a system and we obtain a first order linear ODE. So we can solve that using integrating method or other methods. But it is also possible to get second order linear ODEs, third order linear ODEs, and in general higher order linear ODEs. And solving higher order linear ODEs might not be possible using standard methods. So for that, we have to use Laplace transform. And what it does is pretty much simple. Laplace transform converts a linear ODE to an algebraic equation. And when we have an algebraic equation, it is much easier to solve it analytically. But before we define Laplace transform, let's just remind ourselves of transformation in general. Transformation is manipulation of an existing function, and it could be as simple as shifting that function. For example, let's say we have an existing function fx. If we add fx by 3, the new function gx is just a shifted version of fx by 3 units. Laplace transform is more or less the same concept, except that the transformation is more complicated. And I will shortly describe that. So as I said, the definition of Laplace transform is more complicated, but I assure you, once you try it a few times, it will be quite simple. And in fact, you may memorize Laplace transforms of some common functions. So if I have a function ft, which is in the time domain, the Laplace transform of this function is defined as a fancy L, and this is the notation for Laplace transform of ft, and is defined as improper integral from 0 to infinity of ft e to minus st dt. And for short, we just call this new function capital F of s. And this S is basically a new domain. Most people call it frequency domain. So the only difference between this transformation and shifting is it has a more complicated operation, and it also maps the function from time domain to a new domain, which is frequency domain. So we have a function of t, but when we take the Laplace transform of that function, we will get a function of s. And in order for function ft to be transformable, it should satisfy a very mild condition. And that condition is ft must be piecewise continuous over the range of t between 0 and infinity. And piecewise continuous functions are those that within the interval may have some discontinuity, but in each subinterval they are continuous and they have a finite value at the end of subinterval. So for example, something like that. This is a very general form of piecewise continuous function that I showed, but most functions that we will deal with in this course are much simpler. The simplest function is constant. We may deal with ramp function, or exponential function, or a step function, or impulse function. So now let's start taking Laplace transform of some of these functions and see what we obtain. I would start with the constant function of ft equals a. And if I follow the definition, Laplace transform of a is equal to an improper integral from 0 to infinity a, which is ft in this case, e to minus st dt. And the solution of this integral is a times minus 1 over s e to the power of minus st from 0 to infinity. And if I want to write it more properly, so these two terms are constant. Remember that when we take the integral, we treat s as a constant. So I can factor them out, minus a over s, and then I have the limit of t approaches infinity e to power of minus st minus e to the minus st at t equals 0. So in this case, if t approaches infinity, this term will be 0. And if I substitute t by 0 in this term, we have e to the power of 0, which is 1. So the solution will be a by s. So the Laplace transform of ft is a new function, capital F s, which is equal to a over s. And to give you a perspective, I will draw these two functions ft and fs for a equals 1. So ft will be something like this, and Fs, which is the Laplace transform of Ft, and as I said, it is in the new domain, the frequency domain, which is S, will be 1 over S. So as S approaches 0, Fs approaches infinity, so it starts from somewhere here, and at S equals 1, Fs will be 1. So it will be a function like this. And as S approaches infinity, Fs approaches 0. So the Laplace transform of Ft equals 1 is Fs equals 1 over S. As another example, let me calculate the Laplace transform of function Ft, which is equal to e to the power of minus bt. So again, by definition, the Laplace transform of e to the power of minus bt is equal to integral from 0 to infinity e to minus bt times e to minus st dt. And we can simplify this to integral from 0 to infinity e to minus b plus s times t dt, which is minus 1 over s plus b times limit of t approaches infinity e to the power of minus b plus s t minus e to the power of minus b plus s t at t equals 0. Again, this limit is 0, and at t equals 0, this term is 1. So the solution to this integral is 1 over sb. So in other words, the Laplace transform of e to the power of minus bt is capital Fs, and again I will draw ft and capital Fs just to give you a perspective of how transformation affects the function. For that, I give b the value of 3, and ft will be e to the power of minus 3t. So at t equals 0, this will be 1, and it very quickly approaches 0 as t approaches infinity. On the other hand, the Laplace transform of ft will be Fs, which is equal to 1 over s plus 3. And if I draw this, at s equals 0, this will be 1 over 3. And again, as s approaches infinity, this function approaches 0. So these two functions, ft and capital Fs, They seem to be similar, but if you overlap them, you'll see that ft, which is e to the power of minus 3t, approaches 0 much faster than fs. I think with this I can conclude this session. In the next session, I will teach you more about Laplace transform and its properties and its application.